So for today, about our lecturer. Our lecturer for today is Professor T.K.S. Abam. Professor Tamuno Ene Kingdom Abam is a professor of engineering geology. He holds a BSc degree in geology from the University of Ibadan and MSc GIC London from Imperial College London, and a PhD in engineering geology from the University of Nigeria, Nsukka. Professor T.K.S. Abam was the president of the Nigerian Association of Engineering, Geology, and the Environment between 2017 and 2019, as well as the vice president Africa of the International Association of Engineering, Geology, and the Environment. He is the current director of the Rivers State University Center for Advancement and Linkages. He served for 8 years as the director of the Institute of Geosciences and Space Technology at the Rivers State University, Port Harcourt, Nigeria. Professor Abam's research and practice are both focused on soil characterization, marine geotechnics, environmental geophysics, and coastal hazard. He has published over 100 technical articles in reputable journals across the globe. He runs a region-wide practice as principal consultant in the firm of GrandScan Services Nigeria Limited. Professor Abam is a fellow of several professional associations, including the Nigerian Association of Hydrogeologists, the Nigerian Environmental Society, the Nigerian Mining and Geosciences Society, the Nigerian Association of Hydrological Sciences, the Nigerian Association of Engineering, Geology, and the Environment, the Institute of Oil and Gas Research, and the Institute of Management Consultant. Professor Abam is a Knight of the Order of St. Christopher and is happily married to Barbara Dasika Abam and blessed with children. Ladies and gentlemen, kindly help me to welcome our guest lecturer for today, Professor T.K.S. Abam, for his lecture. Thank you very much. Prof, you're welcome this morning. Can we have your...
Bluetooth now. Yeah. From that, your friend. Take 500.
Prof, do you want me to share it from here?
Yes. Would you share it? Can you permit me to share?
Okay, I think it's on now.
Okay, great. Let me begin first of all by thanking the NMGS Ibadan chapter for finding me worthy to give this talk. I'd like to appreciate those of you who are timely, particularly past President Jim Orife and some other very senior academics, Professor Jaye, Professor Ani Foyoshi, whom I saw on the screen before commencement of the program. Every now and then you hear about building collapse. And when they occur in areas of doubtful soil quality or areas of known weaknesses in soil, there's always a tendency to relate them to either the absence of soil investigation or what we call site investigation or site characterization. Those three words have been used interchangeably very often. But let me say that there are several examples of failed projects, failed civil projects, which, or you can say failed projects or delayed projects, or wasteful projects, which have been due to either the lack of site investigation or inadequate investigation. I'll show you, can you go to the next slide? And I will illustrate this with two examples, one local and one external. Now, what you're seeing is an aerial view of the Langtan Dam. Langtan Dam is in Plateau State. This dam was constructed 1979, and up till today, more than 40 years after, it has not been able to fully impound the reservoir area. The reservoir area has not been filled to capacity. And questions have been asked, why is it so? Was it that the drainage catchment area was not properly scoped? Or was it that there are some structural, could it be that there are some structural features which were not discovered beneath the reservoir area that are responsible for continuous leakage of the reservoir water? That is on one side. Next slide will show you another example, which is the Eurotunnel, which many of us are familiar with. The Eurotunnel, it's an underwater tunnel that links Great Britain and France. That the dominant geology of that area is chalk. Chalk essentially is limestone. Limestone has a familiar jointing pattern. It's like a brickwork. And we all know that groundwater flow in such structural formations are governed by the structures themselves. Now, in an area, the idea of this tunnel was conceived as far back as 1897, but it never saw the light of day until 1997, that is 100 years after. And the reason for the prolonged delay was inadequate understanding of the site. And that's where site characterization comes in. Now, with site characterization, you have a better visualization of the sites. You can anticipate problems. It's a tunnel that is passing, that has about 100 meters of water above, serving as overburden to the tunnel, to the tunnel alignment. And people, because they didn't understand the nature of the hydrogeological problems, research continued for a long time until sometime in the 90s, when a clearer picture was understood that at that depth, it is possible that the hydrostatic pressures, the load imposed by the weight of water above the tunnel was high enough to ensure that the joints will remain closed, having a good control over the hydrological problems. Now, with better characterization, you see that there is better preparedness. You go into an area, you know what kind of geology you anticipate, your timely, your project schedules are timely, so you ensure better delivery, timely delivery. And then the cost, you also, for example, if you have better site characterization, you know what rock types to meet at what time and in what location. You are better prepared with sizing, with your bit configurations and things like that. You know when to anticipate water problems. You prepare for them. You prepare the support and the protection that you need and all that. These are some of the benefits you get. The cost is also better managed. Having said this, can I have the next slide so we can properly define site characterization and know its scope? Now, site characterization has been defined as a three-dimensional engineering geological description of the surface and the subsurface of a location. Now, it's not only intended for environmental remediation, but it could also be required in construction activities, in the engineering works, including tunnels, as I have described, for roads, for railroads, and for dams. I've already given you two examples that involve dams and tunnels. It's also required in projects involving habitation, i.e. buildings, estates, and cities. And then also for harbors, for airfields and related structures, and also for resource development. In mining, you need site characterization to have a better understanding of the distribution of the minerals. So it's also used for energy-related resource evaluation and like that, and also for mitigation of natural hazards, for understanding the for better understanding of landslides and their impact, and for farming, site characterization is required because it gives you a better control over the management of the impacts. And also for groundwater protection, for example, coming closer home, for waste management, as well as for environmental remediation, which is the focus of today's lecture. Can we go to the next slide, please? Now, what are the objectives of site characterization for remediation purposes? Now, remediation comes in when a site has been polluted or contaminated, and you want to be able to identify the nature and the extent of the contamination. Okay, a cardinal objective is that you need to be able to define or to determine the extent of release, how much of this contamination has been released to the environment. Determine the distribution of the contamination in terms of the three-dimensionally. Determine if points of exposure are impacted or potentially impacted. By points of exposure, I mean those areas within potentially contaminated areas that are, that are in contact with man's activities. For example, you have a stream nearby, and there are people who would have to go to the stream, and the stream is on the path of a trajectory of potential contaminant movement. It will be considered as a point of exposure. Or you have a water borehole that is tapping into groundwater that is potentially contaminated. Or you are cropping in an area where you have shallow contamination that can get into the crops and enter into the food chain. Those are all considered as points of exposure. And then it's also important, one of the cardinal objectives is to evaluate all the exposure pathways. When contamination occurs or when an area is polluted, there are always several possible pathways that the contaminant may travel. And then another objective is that you want to determine if active remediation is required. And that means that if the contamination, for example, has no connection with any points of exposure, it is far away from where it could become a source of danger for the community, where it could become moving from the risk stage to a hazard stage, does not exist, then active remediation may not be, or if the level of contamination is low, below the target level, or below the thresholds recommended by the regulatory body, then such contaminations may not necessarily be remediated. So it is expected that site characterization provides accurate information about the presence and distribution of target contaminants in relation to the background environment. And in doing so, it assists in providing effective cost control as well as efficient remediation. Now, next slide, please. Let's look at the requirements. What are the requirements for site characterization? The first requirement is that you need to determine the nature and extent of any contamination, both on entering. Now, when you get into a site, you are given, look, this is the site that is to be characterized. You want to know its boundaries, define its boundaries. Then the next thing to do is what contaminations are coming in and which ones are leaving the site. So it's important to determine the nature and the extent of any contamination, both on entering as well as leaving the site. You also need to identify other hazards that need immediate action to protect public health and public safety and quality. And then you also need to identify and characterize the pathways. I already touched on this, and the targets. And this is where what they call site conceptual models become necessary. Site conceptual models, usually the acronym is conceptual site models, CSM. It's a pictorial. It gives you an idea of the transition from the source to the receptacle, so to say, or to the endpoint, the trajectory. When you have a spill, how does it move? What are the immediate areas? It helps you, it provides a tool for effective control of site characterization and as well as the management of the impacts through remediation. Now, the other requirement is that it helps you determine the needs, whether you have long or short-term monitoring requirements, whether that is what you will need to be able to have effective control of the pollution. Now, it's also required to provide you information about the sources, the pathways, the targets, and if there are other site-specific characteristics, this would help you to permit, it will help you to do an effective risk assessment. And lastly, one of the requirements is that you should be able to provide sufficient information to enable the selection of an appropriate remediation, remedial action. Next slide, please. Now, next slide will give you examples of the conceptual site model. Now, as I said, the conceptual site model essentially is a planning tool. It helps you to conceptualize the relationship between the contaminant, the geology through which it may travel, and the potential exposure pathways. It also helps you to determine areas where data may be lacking, for which additional information would be required to fill the data gaps. Okay. It also helps you to focus data collection efforts. Okay. The conceptual site model, when it is used properly, it helps to it's something that is used at all times. And as you move during the project cycle, you have opportunity to update it at all times. Next slide, please. Now, the next slide is an example of a conceptual site model, which I'd like to explain. Now, this is a scenario of you have a weathered formation on top, followed by a saturated zone, and then you have a fractured rock beneath. There's also a stream. There are water boreholes, and then you have a contaminant source on the surface, which seeps through the unsaturated zone, enters through the saturated zone, and flows further down. The example here is naphthalene. Naphthalene, as you know, is a long chain, and not like bonnet-light. Bonnet-light, it's the hydrocarbon chains are not as long, so they are mostly around the groundwater table. They follow the seasonal variation of the groundwater table, what you call the smear zone. But this is a case, you can see that the trajectory of the contaminant below the saturated zone is controlled by the structures, by the faults and the joints. And then along the line, you have an exposure at the groundwater wells. You also have an exposure within the stream, so that users of the stream are likely to be exposed to this contamination. This is just to illustrate, to give you an insight to how conceptual site models can help you understand the trajectory of contaminants. Can we have the next slide? Now, site characterization is a process itself, and there are six steps or 6 stages. The first stage is to develop this conceptual site model, and then the next one is to define the purpose. Different site characterizations have different purposes, and knowing the purpose will help you set up a decision criteria. And then the next step, this will move on to the development of a data collection protocols. Every site has its own strategy, depending on a number of other site considerations, including geology, topography, and a couple of others. Okay. And then lastly, you now implement the data collection process itself and the analysis. The 5th step is the issuance of a field report. A field report is like a preliminary report. You have done the field work, you've done the laboratory work, you compile your field. It's like a factual report, which is sent to the client. And after that, you now issue a final report, which is more of an interpretative report. Can we have the next slide, please? The next slide has to do with the methodologies of site characterization. Now, over the years, there have been significant advances in the methodologies that are used, involving the planning process itself, the execution, and the tools that are available for deployment in site characterization projects. The choice of suitable suite of tools, reduces the project life cycle and also leads to targeted remedial efforts and reduces the total project cost. We're often told that a bad workman quarrels with his tool. When the tools are not right, you have all kinds of difficulties, in trying to fully comprehend what is happening in the site. Now, the traditional approach for site characterization involves real-time data collection, and I will explain what it involves afterwards, and utilizing that data in making real-time informed decisions as well. Now, next slide. The field activities usually, as I said, the work is easier when the planning has been done thoroughly. So the planning and preparation for field work requires a lot of desk study. You need a lot of desk study. And of course, with the advent of satellite imagery, you can do much more than a routine site visit or reconnaissance visit is able to do for you. You need to plan your mobilization effectively, plan your demobilization, ensure that you recruit the right skilled as well as the unskilled persons that are required. And very importantly, the community. When you ignore community, you are at a great peril of not even being allowed to get into the site. That's the experience we have in Nigeria. And one important requirement is the topography. Now, many of the pollutions we have seen in Nigeria have pollutions that are expressed on the surface. And when pollutions are, even blowouts in oil wells eventually find their way to the surface. So their dispersion, is controlled largely by the topography of the area, But more importantly, many of the pollution events for which agencies have been set up in Nigeria for management deal with mostly surface-related pollution events relating to pipeline ruptures, relating to wellhead malfunctioning and all of that. And when such pollutions come to the surface, their trajectory is controlled largely by pollution. And it's only when you understand the trajectory, it gives you a basis for assessing the immediate risk. You know the transport, the trajectory, where pools are likely to gather, and things like, just as you have surface runoff. When it rains, the same way as water flows on the surface is the way that crude oil, for example, will also flow when it is on the surface in such that constraint. And there are ways. The other tools that are available for site characterization are broadly classified or categorized into non-intrusive as well as intrusive methods. Now, the non-intrusive methods are basically methods that do not require you to intrude into the soil. In other words, to bore the soil, to excavate the soil, and these excavation processes creates, first of all, when you bore a soil, it even creates a pathway for the contaminant to spread further down and possibly contaminate the groundwater. And not just that, when you excavate a soil, the time for recovery is much longer. The communities do not like it when you interfere with the soil condition, because an excavated soil takes much longer to really stabilize and to be able to use. So the non-intrusive investigative tools have what I would call less footprints, in the areas where these investigations are conducted. But about the effect, they may also be as effective as the intrusive investigations. They are usually less expensive, they are faster, so they come in with a lot of advantages. And they would include normally electrical resistivity, some call it electrical resistivity imaging, others call it electrical resistivity tomography. So in the presentation, imaging and tomography may be used interchangeably. And the intrusive investigations are those that involve drilling into the ground, collecting live soil samples, accessing groundwater. And these are usually accomplished using organs, using what is called push-throughs are with cone penetrometers of high capacity that can push and collect continuous columns of soil. There are adaptations anyway, and then current advances in cone penetration technology even have provisions for the in-situ measurement of additional parameters by including probes like conductivity, pore pressure, seismic probes. There are endless, in fact, there are continuous evolution in the technology, and more probes have been added to eliminate the need for intrusive investigations, which are usually more expensive. Now, it is also necessary that monitoring wells, I will discuss in a little more detail the design of monitoring wells for remediation purposes. The logging, a sample collection. It's not every sample that is brought out to the surface that is collected. There must be a criteria, set out to guide sample collection for maximizing information and for ensuring that the right models are created. Of course, between sample collection and results, it's the handling of sample handling for chemical and engineering geological analysis. It's a very sensitive exercise. As you know, petroleum hydrocarbon come in different phases. You have the gaseous phase. There are times when you get at the petroleum, by the time you move from the field to the lab, it has evaporated. The concentrations that will be reported will not represent exactly what they are. So handling is very important. And then the collation analysis of reports and all of that. Can I have the next slide, please? Now, the question is, we've talked about electrical resistivity imaging or tomography. Why electrical resistivity is the question. That's the question many people ask. Now, in trying to understand why this is so, I'd like us to cast our minds on the physical principles guiding a lot of these tools. A lot of us as geologists or as geoscientists, we are familiar with gravity tools for gravity. You look at the anomalies are based on differences in weight, the gravitational pull. And contaminated soils contaminated with hydrocarbon do not necessarily show higher differential weights. Okay, so that knocks off gravity. To talk about the electromagnetic waves, they do not also necessarily show higher densities, where to provide the reflections and all that. That also eliminates the seismics. But however, there are high resolution seismics which are embedded in the ground penetration radar, what's called the GPR, ground penetrating radar, which helps you get very fine resolutions in the shallow, at the shallower level using higher frequencies. Okay. And then of course, also within the electromagnetic wave, you have the gamma ray, which is used for lithological logging, basically because of the presence of potassium, some of the radioactive, some of the soil particles that are, some of the soil materials or elements that are considered ionizing, so to say. And then you talk about electrical resistivity. We all know that one of the parameters used in discriminating reservoir characteristics or evaluating reservoirs is electrical resistivity. In reservoirs, wherever you have, where your wireline logs record high resistivity, you ascribe it to the presence of hydrocarbon. But I will explain why the opposite is the case in this case, in the case of remediation, particularly for aged hydrocarbon skills. Next slide, please. Now, I'll talk about the development of low resistivity. As I said, in the wireline industry, hydrocarbon is indicated by hydrocarbon should manifest as high resistivity. Sorry, can you go? Yeah, okay, that's right. That's right. Okay. Hydrocarbon manifests as high sensitivity. However, after spillage, of course, hydrocarbon is exposed to the element. It commences degradation. It's acted upon by different microbial, bacteria, and all kinds of things come into play. And the degradation process produces some leachates that are highly conductive. Okay, the longer they're exposed to degradation, the lower the resistivity. And that's why contamination, carbon contamination that are in reflects low resistivity. And we have proof for that because within the chemical resistivity that are formed, we have calibrated them, from conductivity or recovered soil samples in order to compare with what the resistivity surveys have revealed. According to Prof. 1998, some of the low resistivity change from and created by the bacterial function of the base of the pathogen. The pathogen is where you have the soil is not saturated, so to say. The soil is limited zone is reduced by absorbed solids. What is possible? The low resistivity shows. Next slide, please. Now, in sampling, let's show characterization. There's every sample that's available on the ground that can be utilized. But it's not that you would have to select a sample with about the volume, the sequence, I got gaps for transporting of this field, and then you do your screen screening, and then you sample and meaningful criteria for what you want as well as analysis. Samples and balance
Dear participant, it's like we're having network issue. It's like we can't hear our guest speakers clearly. Please kindly bear with us.
Next slide. Now, when this gets into groundwater, wrong place. As you know, carbon exists in you have this solid body, this degree, then you have all the organic gas and conductive water. So a bit more solution, that have the carbon against things by any. That's important to measure groundwater. Measure the groundwater direction. Measure the conductivity. Measure the resistivity. And then
hello, Prof. Abam. Hello, Prof. Hello, Prof.
I can hear you.
Yeah, like it's like the participants are not hearing you. The sound is not really good. And it seems to be from your hand.
Really.
Yes. It's really, really bad.
Okay, so let me use.
Oh, I think we can hear you now. It's coming. Nice.
Okay, it's better now.
Oh, yes.
But there seems to be interference. I have to use another tool. So I can move this. Okay, can you hear me better now? Can you hear me now?
Yes, Prof, we can hear you clearly now.
Okay, great. Let's hold this closer. All right, so I said because of the importance of water, some hydrogeologic parameters are also measured. And these would include depth of groundwater, hydraulic gradient, groundwater flow direction, hydraulic conductivity, and transmissivity. And in the end, you're required to also produce maps to give you the regional scope, to understand how the directions of would I say the trajectory of the contaminant and how fast it is moving and where it's moving to, so that if necessary, interventions can be made ahead. Next slide. Next slide are pictorials. We'll give you pictures of some site activities. I'm sure you can recognize some people there. Next slide still. Also pictorial. Okay, this auger boring process. Next slide. Okay, so this is a cone penetrometer which was adapted as push-through for remediation, for site characterization purposes to obtain continuous column of soils for proper characterization. Now, these are, by the right, you have the cones, okay? The first cone closest to the cable is the seismic cone. There are also seismic accessories or probes embedded on it. And then there are electric probes. Some have conductivity, pore pressure, and all that. So as you go down, without the need of bringing out the soil, you are able to measure these things as a continuous depth profile for each of those parameters. Okay. Next slide, please. Next slide is the actual percussion drilling. Some persons have deployed wash boring. Wash boring does not allow you to obtain quality samples because the samples are mixed with water and you can hardly tell what depth they are coming from. However, with percussion drilling, you are able to obtain even laminations, soil samples of small thickness. You will be able to obtain samples and log them. And then it also provides an avenue for you to install monitoring wells. Okay. Next slide, please. Now, concerning monitoring wells, they are typically installed with auger or percussion drilling, or even with push-through. And you require PVC casing, usually of 10 bar, 10 or 12 bar, depending, because at depth, you have a lot of passive, active and passive pressures, which will tend to collapse the hole. But with the strength of the PVCs, you're able to restrain them. Okay. Now, the screens, the choice of the screens is dependent on the soil particles within the range where you are interested in screening. Okay, there's usually a filter design concept which is applied. The filter allows water to come into the hole, but does not allow soil particles. That's the principle. And so after you have gotten your soil samples, you perform a gradation and you plot the part of your filter. Those filters, that's what you procure to use as your filter. And then your wells, you must understand the seasonal variation of groundwater. In Nigeria, groundwater is subject to seasonal variation. It's very close to the surface during the rainy season, at the peak of the rainy season, and the dry season, it gets depressed. Now, because you are dealing with hydrocarbon, particularly bonnet-like, which fluctuates with water table, your screening has to cover the entire variation of groundwater variation, basically. Okay, and your depth if you suspect that there are heavy hydrocarbons, then you need to go further down to be able to track this stuff. So usually best practice is recommended. You select your filter, annulus, and then your grafting. All of this has to be properly done to the best available standards. Next slide, please. Now, these are examples of the different stages of installation. The installation of the screens, the development of the wells, the sample collection using the baler, just to show you. Now, there are usually key issues of concern relating to data quality and confidence levels. Can I have the next slide, please? Now, when you are engaged in this kind of exercise, because the opportunity to be in the field, you might not have a repeat opportunity to be in the field. So at that first encounter, you're required to ensure that there is sufficiency and completeness of data in both scope and quality and quantity. And then that the data collected is relevant to the risk that you are assessing, and that the accuracy and reliability are acceptable, and that data will resolve the ambiguities and the uncertainties that you are likely to encounter. Now, the site investigation process, which is the site characterization, is usually phased. I think I have touched this in passing. Usually you have the preliminary investigation, which involves a desk study, reconnaissance, and sometimes, can you go to the next slide, please? Okay, and then the goal of the preliminary stage is to assess whether potentially contaminating activities, okay, have taken place on the site, and whether soil or groundwater pollution is suspected, and in such cases, and in some cases, to confirm or invalidate the existence of pollution. This phase usually focuses on the hazard identification. And then the next phase is the detailed investigation. This phase aims, the aim of this phase is to define the extent and degree of contamination, to assess the risk associated with identified hazards and the receptors, and and determine the need for remediation in order to reduce or eliminate the risk of to pollution, or trying to protect the receptors. And then lastly, when all of this is done, and there are times when you find that there will be need for supplementary investigation. When you find that from your conceptual model, you find that there are still some needs, some data gaps. You can commission a supplementary investigation to better define the needs and the types of remedial action, as well as monitoring that is required to assess the feasibility of various remediation techniques. Now, we will now go into the phase of case history. The current site characterization efforts, usually, as I said, will involve topographic surveys, geophysical surveys, which are mostly at least in the sequence in which they are applied, okay, to delineate the boundaries, and then the intrusive investigations will come in. Okay, and before you now go into monitoring wells, then the planning and the preparation for remediation, and then you implement the remediation. These are usually the stages up to completion. Next slide, please. Now, the first case history has to do with now this has been gotten from, if you go to the internet, you will see the reports issued by UNEP 2011 as a site called Korokoro Well 3. Additional work has been carried there, which I would like to share. You see that this is the wellhead, and within 100 by 100 meters square, we have to conduct a survey. The next slide will show you the survey, and in the survey, you'll see is pollution actually extended beyond this. I'll tell you what we did in this case. Now, from the topographic survey, you will see that at the center is the wellhead. It gives you an idea of the potential trajectory or surface distribution of the spills, where you expect pools of hydrocarbon, to collect. When they collect, they have time to sit down and get into groundwater eventually. Next slide, please. Now, the next slide just it gives you a little scope as to where we expected the boundaries of the contamination to be. The next slide, still. Go to the next slide, please. Now, following the success of a topographic survey and the outline of the potential boundaries, we had to lay out the electrical resistivity survey lines. The survey lines show you the start points and the end points, and they have also been calibrated. In fact, they have been scaled, okay? And then we have also, in the same plot, we have shown you the auger boring locations, and as well as the monitoring well locations, and the status, the contamination status of from the borings, from the auger and the monitoring wells. Okay. Next slide, please. Now, for each of these resistivity lines, and indeed what we did was the basic Werner configuration. Okay, and you will notice that the lines are not in a gridded format. Okay, but they are made to interconnect with each other, so that it makes it possible for us to concatenate them. Okay, to concatenate them. Now, each of these, you can see the resistivity scale. You see, for example, this is line 2. You can see the variation of resistivity. You see the low resistivity, and then you see the high resistivity. Now, based on the calibration of the resistivity profiles of the resistivity tomographs, normally because hydrocarbon, aged hydrocarbon reflects as low resistivity. Okay, we have a cutoff based on the showing of the contaminated auger borings, as well as the contaminated monitoring well bore, the samples that were contaminated. We found we sort of set a cutoff. We set a cutoff, which now enables us to define the surface distribution of contamination in 2 dimensions. Okay, so this is one example. This example utilized what a software called RES2D. That's to say, it's a resistivity software that comes with basic resistivity equipment. Okay, now this using the same set of data. Next slide, please. Using the same set of data for the same line, using a different software called Earth Imager. Okay, we generated the same tomographs or images. Okay, in this case, you can see the same resistivity profile. You can see the index, showing you the different resistivity ranges, what resistivity represents which color, and then after we apply the cutoff, you will see this. So you can compare this to the immediate last image to see what differences are introduced by the software in terms of the resistivity, the analytical resistivity imaging, so that it becomes easier to fully appreciate. Next slide. Now, these images were also run across areas where we know pipelines to occur. And you can see in the images that it even picks up the pipelines. You can know the depth, you have an idea of the diameter, and all that. So this what gives confidence. In addition to the auger boring, retrieving samples, measuring their resistivity, knowing their contamination status, and relating it to the lines, where they are, and comparing it with the resistivity values that are recorded or reported by the parameters, to build confidence in the process. Next slide, please. Now, after all of the 2D resistivity images have been generated, we now have to go through the concatenation process. Is the process of using the 2D images to build a 3D tomograph, so to say. Okay. Now there are softwares. There are 3D, REST 3D software. There also the Earth Imager also has a 3D version using the same data, and we will compare that so that you can see. Okay, here cutoffs have not been applied for that Korokoro trade. You can see that this is the outlook of resistivity and contamination at depth 1 at 1 meter, for example, and it's overlaid over Google, so you can relate it to some footprints, some landmarks for guidance. So when remediation is being done, you know exactly where you are, and you can relate it to existing landmarks. Okay, next slide. Next slide is you can obtain for any depth of interest. If you want detail, as much detail, you can go sequentially 1, 2, 3 meters and all that until you get to your target depth. This is for 5 meters. Okay. Next slide. Now you can see the shapes. You see that the shapes are to show you the extent of penetration of the contamination, which was also confirmed by the bearing. Now, this is the same imagery, but produced by Earth Imager, okay, a different software, which shows more or less the same thing. Okay, next slide. Okay, so this is for 3 meters using Earth Imager. You can see that the shape of the profiles of the tomographs are changing a bit to reflect the distribution, the vertical distribution of contamination. Next slide, please. Next slide, still. Now, this is 8 meters. Now, at if you recall the slides where I showed you the monitoring wells, the auger boring, you see that the augers were, I don't remember what slide that is. The augers were stained by crude. You could see a bottle that was stained by groundwater contamination. And when there was a free phase floating on groundwater. The depth to water table there was about 7 meters. Okay, 7 meters. This meant that contamination had gone from the surface through the different soil ecological sequences down to groundwater, and it's now being transported by groundwater. Okay, but it may not be in an even way. There are some areas, because of the presence of less pervious soil, the crude could not penetrate further, but in some other areas, you find that there is penetration down to groundwater and perhaps deeper. In fact, we've got contamination up to about 12 meters in some cases, and it left me wondering whether these crudes are mere bonnet-like, which was expected to be within the smear zone, which is the area within the variation of groundwater level, the seasonal variation of groundwater level. And it led me to wonder whether there are other longer chain carbons that are embedded in that spill. And you recall that at the time that this spill occurred, they were still using barium and diesel as in place of they used it as drilling fluid in place of bentonite. So you find that there are some areas, I will show you that graphics, where we also looked at the concentration of barium, and we found it concentrated somewhere around the wellhead, which meant that that this was the case at that time. But I think with improvements, they went away from those practices. So next slide, please. So this is 12 meters. You can see the presence at 16 meters. It shrunk further. It became even discontinuous to some degree. Next slide, please. Now, there are provisions where you can measure at any depth. at any depth, you can determine the surface area. Sorry, you can determine the area of contamination. Now, this helps you not only to determine the surface area, but to also evaluate the total volume of contaminated soil. It helps to bring some degree of precision. Now, usually, what would happen is that you tell a contractor, go to this site, you have to remediate X length against Y length, usually, without knowing the shape and structure of the contaminant. So this is the sense, this is the way in which site characterization brings something like, surgical precision to quantification, to control cost, timely delivery, for visualization, and for full management. Can you still hear me? Sorry, what has happened? What has happened? Can you hear me still?
We're hearing you.
Okay. I'm not seeing the images again. That's why. I'm not seeing the images.
I hear you loud and clear.
What? Okay, so can you see the slide from there?
The host changed.
The what?
Cannot show you at all.
The host changed. The host.
We can't see the slides, sir.
Why don't you? I should show my slides. Okay, let me show my slide. Okay. Yes. Can you see the slide now?
Yeah, we can see the slide.
Can you see the slide now?
Yes, we can.
Yes,
okay, great. Now
you can start slideshow.
Okay, so during augering, this is the slide I was actually referring to. This auger by your right is so stained. You can see the soil looking so like it's like palm. The stains there are hydrocarbon. This is a well not far away, separated from it by a road. This road was built as an access road to the facility. I will explain why the situation here. Here, the contamination is in dissolved phase. It's in dissolved phase. The water is clean, but when you put a dip meter, if you send in a dip meter, there's no reading. It doesn't give you any sound to indicate the contact with water. But when you put the dip meter in bottled water, it sounds, which means that in the world that is, and indeed, laboratory testing of the water, of the groundwater, confirmed that that it was contaminated. You can see somebody's hand here showing the oily water. You can see by the right, bottom right, you can see me there with a bottle of this thing that is so badly stained. That water is, the groundwater table there is about 7 meters, and there is free phase of water there. Now, the borings normally will result in logs where you indicate the lithologies, the sequence of lithologies, the water table, and the contaminations, whether it is heavily contaminated or whether it's just a sheen and all that. There are for both auger boring as well as for the monitoring well. And that's how these ones are prepared, so to say. Now, in using these little logs, we have to use these little logs to generate a fence diagram. To generate a fence diagram where you see the lithological diagram, and you can view from different perspectives, from, to give you a holistic idea of what soil occurrences, which, where is the hydrocarbon in all of this. Now, what we went further to do is to generate add another layer to include the contamination status and the depth horizons covered by this contamination to help us generate an additional layer. So here now, you have the fence diagram superimposed on the distribution of contamination as observed in the auger boring as well as in the monitoring well samples. Okay. Now, what we did now to have a good control is to overlay this information on Google Map, so that when you see, this is the road I was talking about, that's a borehole where you had a free phase. It's in this building. That's I don't know if you are seeing the cursor. Can you see the cursor? Okay. Okay. Can you see the cursor? You can't see the cursor.
Yes, Prof, we can see.
There's a white roof there. Okay, that's it. So that's there. That's a road here separating it. And my understanding is that this road the road runs across.
Prof, can I start projecting from here so that people can see clearly?
Okay, you can
Okay,
start that.
okay,
I'm almost rounding up.
okay, you can continue,
Okay.
sir.
Okay, so there is a road that runs across there. You can see the put on Google imagery. The theory is that's my own interpretation of what may have happened, is that the roads of those days, you have the topsoil is excavated, recompacted before you put an asphalt layer and all of that. Heavy compaction is usually carried out. That compaction would have diminished or would have reduced the permeability significantly, such that horizontal, transmission, was discouraged, and that's probably why the contamination did not spread significantly westward. I mean, not westward. Okay. So next slide. Now, this is another case history. This location is called Egbalo, so it's also within the Ogoni area. Clearly, this is a pipeline, and you can see the resistivity lines, the starting points, and you can see. Okay, went for that. So from this second case history, you will see that from a plot of the auger borings and their contamination status, this is what we had. The hydrological modeling produced what is in the middle, and then the resistivity tomographs, the 3D resistivity tomographs produce what you have here. You can see where the differences lie now. The resistivity tomograph makes some assumptions, some continuity. In fact, one of the differences between the RES3D or the RES2D and the Earth imager is in the sharpness of the images. In the RES3D or in the RES2D, you find that the images look too vertical, very sharp. In other words, we know that fluid flow in porous media follows a natural curvature. And that is why you have a flow, that's why you have laws governing the flow in what you call flow nets. You have the equipotential lines as opposed to the flow lines, but in the RES2D, you don't have that. Whereas in the Earth imager, there is some smoothing of the path. Can you still hear me? Has it gone off?
Hear you. We can hear you, Prof.
Can you still hear me?
Yes, Prof.
Okay, great. So can you go back one step? Where am I now? Can you go previous? Let me go previous. Okay, so in the slide that you have the contamination polygon. So even for this case, you are able to determine, depending on your depth of interest, to determine your area of contamination. Okay, it's connected. Progress. Okay, can you hear me now? Do I need to share again?
We're hearing you.
We are hearing you.
All right.
We're not seeing any.
Okay, so can you see now? I'm sharing now. Okay, so Dr. Dada, can you share? I have just a few slides now to close. Hello, okay, so can you see now? Dr. Dada, can you share?
We can't see. We cannot see anything.
Recording in progress.
I think the issue is from the person that is sharing the slides.
I'm sharing now. Okay, so you can see this now. So, as in the previous case, you can also determine using what they call a software called endpoint, determine using the polygons to determine the area to a high degree of precision. Next slide. Okay, then you can also determine your groundwater flow direction, you know, from the monitoring boreholes. You can do your generate your spot height, and then your depth to groundwater table. You have your reduced water levels, and then you generate your groundwater flow direction, which gives you an indication of where the contaminant, the free phase, is going. So it helps you to determine where to introduce intervention in order to limit the spread of. Now, what we did was looking from laboratory analysis, we generated this is the distribution of TPH, for example, okay, and it follows the topographic trajectories. And just to give you an idea, from the lab also, we also had to determine the contaminants at different depths, and we found that the contamination was concentrated in the smear zone. Here, at the time this was done, groundwater table was around 5-6 meters. Okay, so you can see that the peak of the contamination is here, which means that the contaminants went down, okay, assisted by its own weight, by water infiltration pushing it down. And once it got to groundwater table, the seasonal variation of groundwater now moved it up and down, concentrating it within the smear zone. This pattern was repeated in most of the wells, as you can see even from this. Okay. Now I looked at looking at all of this, we developed a criteria for design of monitoring wells, particularly in these areas, based on the lithological sequence, the nature of the distribution of the contaminants, the groundwater seasonal variation in groundwater, and we are proposing that for monitoring purposes, your screens must straddle down. Okay, the topsoils are reasonably free of contaminants. So once you pass the topsoil, your screens can be installed down to a few meters below the low. That's the groundwater level, dry season groundwater level, more or less. And that gives you a good grasp of the movement of contaminants in that area. So by way of conclusion, I'd like to say that site characterization is imperative, as we have also, for understanding the extent, shape, and distribution of hydrocarbon contamination in an area. Okay, and we are saying that it should be recognized as a necessary first step towards designing an effective remediation measure. That approach where you just come to remediate this area without understanding the extent, shape, and structure of the contamination is wasteful, it's cost expensive, and it's time consuming, and it impacts on the value of the land. The value on the land. Now, site characterization also provides a basis for quantification of contaminated volumes, for remediation, and in that way, it brings better precision, almost surgical precision, and also makes the whole process more economical. Okay. And then electrical resistivity tomography It deserves an increasing attention since it is a low-cost, high-resolution technique that can rapidly image the states and processes. And fourthly, the comparison between the ERT and the methodological modeling, which we have seen, shows that the ERT can be reasonably reliable, depending on the choice of your resistivity cutoff. And lastly, when you repetition of the characterization process using the ERT with time intervals, when you do it over time, will help you monitor changes at a contamination site and determine the effectiveness of an eventual remediation process. Thank you very much. Thank you. Thank you. Thank you.
Thank you very much, Professor Abam, for this well-researched and delivered lecture. And we equally want to appreciate our distinguished participants for this particular lecture, for your attention and also for your patience. Now we have, the floor is open for our distinguished participants to ask questions or probably to make contribution to the lecture that has just been delivered. So you have the floor. You can ask your question, or probably you can type it, and then we read out to our guest lecturer for today. So can we have our distinguished participants? If you have any question, the floor is open for you to ask your question. Questions? Questions? Yes. Any question from our participants? Okay. Can we hear from? Okay. Okay. Thank you.
Good morning. How are you? How's everybody? Thank you, Professor Abam, for the great lecture. It's very impactful, and we have learned, as for me, I've learned a lot. I just want to ask, can we get the seminar papers so that we can be referring it to, the seminar paper or the lecture paper? Please, thank you.
Thank you very much, sir. That will be made available on our platforms, the NMGS National and also the NMGS Ibadan chapter WhatsApp platform. This document will be made available. Thank you very much. Okay, we can see Abib Ibrahim raising up his hand. Abib Ibrahim Adamu, you have the floor, please.
Good morning, good afternoon, rather. Thank you very much, Prof, for that beautiful presentation. I really enjoyed it. My question, sir, is I'm looking at I'm joining in from Sokoto. I work with Osman Dabur University, Department of Geology and Osman Dabur University. So I was looking at this the conceptual site modeling. Is there how we can apply it towards mitigation rather than remediation? Because for the inland basins now are getting a lot of interest in terms of oil exploration and all of that. So I was wondering how we could, harness this knowledge to try and have some models of these basins so that it will inform the decisions while the exploitation is going on, so that at least we will not be making the same mistakes we have made in the Niger Delta. So I'd like Prof to just shed some light on that, and let's start thinking about the possibilities of how this can be done towards mitigation as well. Thank you, sir.
Hey, Prof, would you like to attend to that question? Professor Abam.
Yes, thank you very much, Ibrahim. Now, the conceptual site model, as I said, it's a planning tool. It's a tool that enables you visualize the problem, anticipate problems, identify areas where further work is needed, or further data is required, And I think overall, it helps you to, reduce the impact of your project. It helps you reduce the impact of your project. So in terms of mitigation, it helps you reduce the footprint. It helps you reduce the potential impact, the potential adverse impact of the project. I think that is the way to look at it. If you're looking at lessons learned and trying to apply it to inland basins. That is the way I would like to look at it. Otherwise, it's a tool for characterization to make sure that you have an optimal model that helps you ensure economic deployment of resources, helps you prepare, in anticipation of a potential problem. You already have the tools ready to tackle it. It gives you a better perspective of the environment, that you're going to. Don't forget that it's an engineering geological tool, that facilitates remediation. If used, but site characterization is not only used for remediation. As I said, there are other services in construction, energy resources utilization, waste management, and so on. So that is the sense in which I'd like it to be used. Ibrahim, I hope I have addressed your question.
Thank you very much, Prof. And also we have some questions, I think maybe I need to read it out from Professor, our dear Professor G.O. Adeyemi. I think is asking a question. I can't. Prof, I can't. But okay, now I think there is another comment. Thank you very much, Prof, for your lecture. In places like Niger Delta, is it possible to differentiate between the contamination from seepage and the natural near surface hydrocarbon? This is coming from Tony Shukuma. Prof, I think this needs your attention. Do I need to come again?
Yeah, you asked.
Is it possible to differentiate?
Good afternoon. Good afternoon.
Yes,
Good afternoon.
Hello, Prof. Can you hear me?
Yes. Well done, my
Hello,
friend.
Prof.
Professor Abam. I want to appreciate you for this very standard lecture. And I am not surprised because you are used to delivering standard lectures over the years. I just want to get some clarification. Because you are using the term contamination. But I am not an applied geochemist, but I know that there is a difference between contamination and pollution. I think we'd like you to let us know the difference between the two. Again, in developed cities in Nigeria, even in rural areas, we have waste generated, day in, day out, as a result of rapid industrialization and even population growth. And we are always concerned with groundwater. I remember you also talked about groundwater. There is need for us to map pollution plume, especially of leachate from waste dump. I know we can use electrical resistivity, especially horizontal profiling, and we can also use chemical analysis. This is just a way of contribution. I know that you are in the Niger Delta, and you are focused on the activities in the Niger Delta. But whether Niger Delta or other parts of Nigeria, we have waste generated in each volume, both biodegradable and those that are not. That's just my contribution. Well done, and God bless you. Thank you very much.
Sorry, can you please ask, let past President Jim Orife speak before I answer the questions, please.
Okay, our Papa is on the line. I mean, it's online. Our Papa Jim Orife. Sir, you have the floor, sir.
Thank you very much. Thank you for your lecture, Professor Abam. I'm happy that you gave this lecture because it shows that we are beginning to appreciate what we need to do is subsurface. My question simply is this now. With all what you have said today, I have been quite, I have learned quite a few things today. The ministries of environment and all those other establishments that are concerned with pollution, especially like the Ogoni one, for instance. Was this process used before the HYPREC started working in Ogoni, or the other when they started excavating? And in the other ministries where environmental issues are concerned, are they deploying such measures and knowledge to assessing such situations when they occur, or they just go and do what they want to do without any technical input? Thank you. I don't know where you go what I said.
Yes, I did. Let me
all the work we have done has to be benefited from for it to be useful, because all the work we've done, if nobody is using it, then it is just like wasted intellect. So I think we must find a way of pushing this thing to either the environmental monitoring organizations or ministry of whatever ministry has to do with environmental protection and what have you, to be able to have it so that we can protect the environment and protect our underground waters and other things that we need to do with things like this. For instance, when they are doing walkover on wells, when they leave, do they ask for suggestions to be done for them, or they just leave and just say we are gone? Thank you.
Thank you very much. Let me just begin from the last one, and then I will, after that, talk to Professor Adeyemizu, and then the sir, when HYPREC began, we did the first pilot project on site characterization for HYPREC. And prior to that time, it was a little ad hoc, and it didn't follow this format. Electrical resistivity tomography was not utilized. They did random augering. And I think that's part of the reason why we had to really research into this system. And we made a success. Even HYPREC considered it a breakthrough and innovation in their practice. And I think they have resolved that moving forward, this is the way to go. Now, I know that the Federal Ministry of Environment supervises all of the environmental impact assessments. Before, as we all know, before any major project is done, an environmental impact assessment is commissioned. And part of the environmental impact assessment, some form of site characterization is done, that which is the physical environment, okay? But it's tied more to groundwater. The scope of the characterization done as part of the EIA, which is what the Federal Ministry of Environment does, is very limited. I think there is need to expand it. Yeah? That is other ministries. I think that I have also implied here in discussing the scope and applications of site characterization. I have suggested that there are wider applications wider applications than the hydrocarbon remediation or pollution in mining, in energy environment, in construction. I think as a standard practice, we need to begin to expand the scope of these services. You know, I think that is also the way to get us more involved, to create more sophistication in our practice, and to make our work more relevant to other sectors. Now, to Professor Adeyemi, he asked the difference between pollution and contamination. I will say that it's a matter of degree. Contamination, when water is contaminated, it means that the water is not pure enough. You know, there is foreign elements in the water. That is contamination. But when there is too much, foreign element or too much crude, then it's pollution. So that's why I said it's a matter of degree. Contamination, this Coca-Cola is contaminated. It means that there is something that should not be there that is there. But if it becomes too much, and you could say that that thing is polluted. So it's a matter of degree. And then the other one has to do with is it contamination? Sorry, mapping of pollution plumes. Yes, electrical resistivity tomography has been applied to map the plume of waste dumps. As you know, particularly in this part of Nigeria, we have a high groundwater level, and most locations in the Niger Delta may not be as suitable for as waste dump sites. Okay, our waste, what do they call them now? Waste dumps are not engineered. No special effort is made in lining them to make sure that you stop leaches from permeating into the groundwater. But I'm aware of some studies in which electrical resistivity imaging or tomography has been applied successfully. So to map plumes, leachate plumes from waste dumps. So that is possible, and it's already ongoing. I've seen students, I've examined students who have done that, and I think I'd say I'm satisfied with the degree of work, although more needs to be done. Particularly, the ones I've seen are mostly in the Niger Delta. I think that others can also practice the same thing so that we can move forward. Thank you.
Thank you very much, Prof. But before we invite the chairman, we have a message from Abdul Jalil Subai Dangata. He said, "Thank you, Prof, for the lecture. Even though I joined late, but I was able to be brain-fed. In the place I come from, urbanization affixed cemeteries to a closer proximity to houses and domestic water sources, such as hand-dug wells and boreholes. So how can we use this conceptual site model to investigate a possible groundwater contamination?" This is coming from Abdul Jalil Dangata. Prof? And also maybe, do I go ahead and read other questions, or you want to attend to this particular question, Prof?
Yeah, I think you can go ahead to read it. We were talking about
okay,
CMS,
this is coming from
the
Kendi Akinteriwa. Prof, sir, do we now conclude that pollution is of a higher degree than contamination? From Kendi Akinteriwa. Do we now conclude that pollution is of a higher degree than contamination? This is coming from Banwo. All pollutants are contaminant, but not all contaminants are pollutant. Okay, let me just allow Prof to shed more light on this question.
Yeah, like before, I start from the last. It's a categorical yes that pollution and contamination is a matter of degree. Yeah, it's a matter of degree. as I said before, all when you have pollution you have extreme contamination. It has to be extreme, you know, for it to become a pollution. To pollute means you are partially altering the configuration of contamination retains essential elements of the substance in question. You know, if you say your water is polluted, it means that the degree of contamination is extreme. So it's a matter of degree. I'll say a categorical yes to that. And then the other question has to do with how you can use the conceptual site model in understanding whether your borehole is contaminated or not. I hope I'm right. Is that the idea?
That's true,
Does that
Prof.
make sense?
Yes,
Okay.
yes, sir.
So, now, the conceptual model is basically a tool. As I said, it's a planning tool. It helps you conceptualize. It helps you to visualize. The construction of your conceptual model draws information, relates the contaminant, in other words, the source. It looks at the geology. It looks at the exposure. In this case, depending on the contaminant, I don't know where he's coming from. Maybe there's a waste or a sockaway close by, and he has his water borehole, okay, and he wants to see what the relationship is. Okay, you have the source. You have to understand, first of all, what kind of geologic formation, exists between these two. Yeah, the distance from your source to your exposure, which is the water borehole, the nature of the contaminant, how far it has gone into the soil. Has it reached groundwater? What's groundwater flow direction? If your exposure is on the pathway, if your water well is on the pathway, then all of this, you can even compute seepage. You can compute the travel time, how long it will take for the contaminants to get to the exposure point. And that will give you increasing confidence as to the risk and potential hazards that lie ahead. So it's possible, okay, that a good conceptual site model would help you fully grasp the risk that you face in your borehole. Even when you have multiple sources. We live in places where you have streets. Every home has a borehole. Every home has a sockaway. We don't know the condition of these sockways. Some of them are aged. Some of them may even be fractured, maybe in terrible state. And you need to, I think such a study is overdue, particularly in densely populated cities. So we can understand the risk that we face and make a case for a proper septic waste management system. Maybe we can have central treatment units to avoid an epidemic. These are some of the things that can, that spring up as a result of this discussion on the conceptual site models and the risk to society and human health, particularly, and the protection of the environment too. So that's my response to that.
Thank you very much, Prof.
Can you allow Dr. Kayode Adeolu, President of NICWS?
After Dr. Kayode Adeolu, I will allow our chairman of the chapter, Dr. Olubumi Adeigbe, to take over after the response to Dr. Kayode Adeolu. Okay, Dr. Kayode Adeolu, you have the floor.
Well, I want to thank Professor Abam for a well-delivered lecture, a thoroughly researched work. I really enjoyed, though I joined a bit late. I really enjoyed it. My own comment is more like a comment and question per se. Is considering the fact that the delineation of the contamination is an active thing. It's not like it has contaminated and it has stopped. You would agree with me that depending on the permeability characteristics of the subsurface, it will determine whether the activity of that contamination is still continuing or it is stagnant. Would you not also look at the possibility of periodic measurement, taking this periodic resistivity measurement to form a kind of a 4D time lapse to be able to ascertain the trend and the rate at which this contamination is going beyond the shape as identified in your delineation? Because, for example, what you gave them now, they may not even start working on it, the remediation process, in another 3-4 months or even a year. And at that time, they want to come in to take this data as a guide. Would it not be necessary that there is a periodic measurement in these positions to form a kind of 4D time lapse, sir? That's just what more like a comment or a question. Thank you, sir.
I think that mentioned it in my conclusion that periodic measurement will give you an idea of changes that may have occurred in terms of requirements, in terms of water regulation. For example, based on the work, the application was commissioned to come back again and then perform the exercise. The training that have taken place, whether the application has been done properly. And then if the application has been done, do it as I want to do, whether some additional movements have taken place, change, and then by the time interval, you can give an idea of the rate. And I'm trying to recall. I said that when you want to see the ground, you want to elaborate. Layer. Helps you to do an analytical model. Okay, take place.
The audio is gone, sir. Your audio is gone.
The audio is gone. All right. So I said that. Can you hear me now?
Okay.
Can you hear me now?
Yes, yes.
Okay. So I said that I had mentioned some of the things Dr. Kawade mentioned in the conclusion, that periodic measurement is necessary to know changes in the process, to know whether there has been movement, to also determine the success of remediation, okay? And that additionally, it is the reason why physical and chemical measurements are taken. The physical measurements can include porosity and permeability, maybe even empirical permeability using hazing or any of these empirical relationships. Okay, you can now generate a permeability layer, which will now help you determine infiltration, the spatial distribution of infiltration rate. Okay, so if there's a spill here, you can determine the rate at which each one will go. So intercept the groundwater and all that. And I think it's even for theoretical purposes, it gives you an additional confidence, to know which areas are potentially protected and so on. Thank you. Thank you, my president.
Thank you, sir.
Please, do I have the floor now?
my chair, you have the floor, sir.
Okay, thank you. Let me thank the Professor T.K.S. Abam for a well-researched paper and for a wonderful delivery. Indeed, you are a teacher of teachers, and you have demonstrated that today. So on behalf of the NMGS Ibadan chapter, we want to really appreciate you and thank you. When I told you that this is what we have in mind and stuff, you did not hesitate to say, yeah, I will be available, I will do it. Never knew it would be this powerful. And I want to believe that everyone that are into engineering geology, especially in the sedimentary terrain, will agree with me that he has done well. So once again, we want to appreciate and thank you for a wonderful job well done. Also, I want to thank all the participants. As of the last count, I can see we have like 38 to 40 people online, especially Baba, our mentor, our leader, Baba Jim Urife. Since we started this Ibadan chapter virtual lecture, he has always been online and he will make comment so that you know that he has been part of the lecture. So I want to really thank you for giving us that courage, that, impetus to continue when we see people like you, with us. So we thank you for having time to participate. For all the people that participated, especially the president of NICWS, Dr. Adeolu Waliu, for taking his time out to join us on this platform. Thank you so much. I want to say this, that come December, by God's grace, we're going to be having another presentation. It's a quarterly thing, and we're going to be having another presentation. And I want to believe that you will join us, and I can assure you that the person we're going to bring, you will enjoy his presentation, and he's going to add value to your knowledge, to what you know already and what you need to know, and the next trend in the area that we are going to focus. Having said that, I will hand over back to the chairman of the lecture, Dr. Shegun Dada, to bring us to a close on this presentation. Thank you.
Thank you very much, my wonderful chairman, for that brief vote of thanks. I really want to appreciate our distinguished participants. I could say that Professor Pafunshaw, the COMED registrar, was online, and also Professor Wulabi Ajayi, and also Professor Anifuwoshi of Futa was briefly with us, and also Professor Adeyemi of UI. We really appreciate everyone. We appreciate you for your time, for your patience, for being part of today's lecture. We really appreciate you, and we hope to see you again. Thank you very much, and God bless you. Thank you. Yes.
Thank you.
Sir, we didn't lecture any woman.
Bye-bye.
No woman is appreciated.
We also,
No woman is appreciated. So we don't come.
we also appreciate all our women for joining and being part of it. Thank you so much. Thank you so much.
We greatly appreciate our mothers in the house. Thank you very much, Ma. Thank you for being part of this lecture.
God bless you all.
Well done, well
Thank
done.
you very much.
Yes.
Thank you, Professor Abam.
Thanks
We
a lot.
appreciate you, sir. Thank you.
Thank you.
Thank you, everyone. And thank you. Okay, bye for now.
Okay.
Bye.